Okay, so hello, good evening, and welcome to Physics for Students. My name is Shaunak, and you're watching live lectures on topology. And we would continue our understanding of topology today, and we'll try to look into what is called the topology and topological space. Now, before I begin, I just wanted to make one point, very clear is that the idea of topology or whatever the topological space, etc., that we are looking into, this is a kind of a, I was telling, it's a kind of a shift from a particular system of coordinates to another system of coordinates. So whatever is happening out here is, a kind of a very generalized system. We're trying to get rid of any kind of a metric system, any kind of a definition of notion of idea of distance, etc. So there is another topology which is called metric topology. And yeah, Praveen, very good evening. There is something which is called a metric topology. We will look into that, but we are basically looking into what is called a generalized topology. So earlier, I mean to say yesterday, day before yesterday, we looked into the concept of topology. What is topological invariance? Why do we need a topology? How topology is going to take a shift in terms of our career, in our understanding of coordinates, etc. And today we are going to look into what is called the concept of congruency. Now, when I talk of congruency, what I'm trying to tell you is that when we talk of Euclidean space, yeah, Thomas, very good evening. Logging in from Germany. Welcome. So, Rajkumar Mukherjee. Yeah, very good evening. Very good evening, Rajkumar. Yeah, Vishnu. Okay, yeah, very good evening. Vishak Dutt. Okay, you are reading about general topology. Okay, Introduction to General Topology, K.D. Joshi. Anyway, I have not read about this book. Must be a very good book because if you're reading. Maida Rahat, very good evening once more. Okay, so after all those good evening, let us start a good topology class today. Okay, just a quick note, as I go on talking on this, just put it in the chat box. How many of you are really willing to learn tensors? I mean to say tensors as a whole, as a course, the mathematical aspect, the intuitive aspect, the geometrical aspect. I'm not saying that we will solve problems on tensors, but how many of you are really serious to learn tensors chapter by chapter, maybe once or twice a week, say 30 minutes or so? Please do let me know in the chat box. Tensors, tensor calculus or tensor analysis, whatsoever. Okay, Praveen is telling you want to know. Okay, let me see how many people say. So the concept of congruency, now we are going to see that how it shifts to the concept of topology. Okay, so, okay, Vishnu is also going to. So the concept of congruency changes. How the concept of congruency changes, that is basically what we are going to look here. And we are going to understand, again, a kind of a shift. Because as I told you, 2-3 classes will be required in order to know what is topology and what are the things that we need to know. So here right on the screen, you see these are basically the concept of congruency that we know. Angle, angle, side, 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 right hand side, then the 90 degrees, the orthogonal angles, etc., everything. So they are congruent to each other. I mean to say the concept of congruency, you see they are related to each other. Now here again, I would like to show you my Jamboard, because there is a reason for that. So all those things that we have taken, I mean to say for example, if I take, where is the shapes? Yeah. So if I take any kind of a shape, I'm not taking square for a definite reason. So if I take any kind of a shape again, okay, so let us take any kind of a shape like this. So we, whatever the angles and the sides that we get in, for example, this one and this one, as I told you, this angle followed by this angle and this angle, distance from this particular point to this particular points. Again, they are a very, what I would say, again, very, very local in nature. All of them are very local in nature. Now, what we are trying to do is that we are trying to get hold of a kind of an absurd shape, as I told you, very, very absurd shape, etc. When these sides are actually broken or they are bent or they are twisted, we'll get there. And then we don't need to find out the angles, congruency, etc. We can just find out the properties of this particular abstract shape, properties of this abstract shape, and then we can easily extract what are the properties of those other shapes. Now, as you see that when I'm trying to extract those properties, then obviously there has to be something very typical to these polygons. Okay, there's something which is very typical to these polygons. So if it is that polygon has no holes in between, there are no holes in between, then possibly this abstract object will have some kind of a property without any holes. If it has got one or maybe two holes, then we can distinguish that means somehow where we are trying to get a family, I repeat this word, a family of objects which carry the same kind of a shape and size, which can be again studied in this kind of a shape. So that is the idea. Okay, Vaishak also wants to know, Myra also wants to know. Okay, great. Okay, so from here, as you see that the concept of invariance is also there in Euclidean space. That is, the angles are congruent when they are flipped. Okay, so you see the 30 degree is maintained even if I'm flipped. If I rotate it, maybe that angle 180 degrees is also the same as 180 degrees. So this is what is called invariance. Now, here is the question. Here you can see, can we devise a tool where all these polygons are invariant under changes? I'm to say any kind of a tool where we rotate this, we bend this, and also area is equal and shape is different. No, it's not going to say area is equal. No, not area. We are not at all concerned with area. Yeah, Shabir, very good evening. It is not a question of area. I mean to say the internal property would be the same. I will come to that. I know why Vishnu is asking this question. It's a very good get. It is not that the area, because we are not worried about at all by area. The reason we are not at all worried by area, Vishnu, is that again, when we talk of area, that means area of what? Area of a sphere, area of a, area of a square, area of what? Again, so we are not confining ourselves to any shape. So the question of area, the question of distance, the question of angle will parallel or etc. not there. Are you getting my point? So that means here you see all those polygonal shapes are now deformed into any kind of a topological shape. So all these polygons, as you see, I can deform or change it to any kind of a shape. And that is why we call this high and by. Maybe next time, full session, best regards. Nicholas Caldernisio. Okay. Okay, fine. Yeah. So this shape, so that is why this side is there. So polygons are replaced by any shapes, and congruency is replaced by topological invariance. Here it is, polygons are replaced by any shape. So here you see, as I show you, these are polygons which are replaced by any shape. And most importantly, congruency is replaced by topological invariance. This is super important. That means if I say that this angle or this side is something congruent to this side, or this angle is congruent to this angle, we say this one is congruent to this. We use these signs, angles. Okay, so this will be something which we call it as topological invariance. So this would be topological invariance. So topological invariance, try to understand what I'm trying to make a point. I know this is a little bit counterintuitive and a little bit invariance. Yeah, a little bit difficult. But so topological invariance, I mean to say, whatever we are trying to say, it is to specify, if you specify points within the figure. Yeah. So the thing is that whenever we are trying to specify anything, rather than I extend it to a kind of a, I would say, superset, where we are not talking of congruency of each particular line angle, but you're talking of a general whole set, which is called a topological invariance. Here I use the word set, and that is why I told you yesterday that I will tell you why do we use set theory. Let me show you, then we will move to that. Because this might be a question that why we don't use calculus. Yeah, that can be a very good question. I mean, so why we don't use differential or integral calculus in order to understand topology, but why we are using only sets. So this definition, oh, I'm so sorry, to skip this part. So this definition that when we are this was for the my other channel. I was teaching tensor calculus, so that is why I asked you that these are actually screenshots from that particular channel. Okay, so what I was trying to tell is that when we move those kind of shapes, okay, when we move those kind of shapes, any kind of a shape into a kind of an abstract shape, I will just show you once more so that you can understand. When we move all those kinds of polygons, etc., to a kind of an abstract shape like this, okay, anything like this, when we are moving all those things into this kind of a shape, that means it is something which we are calling topologically invariant. Topologically invariant means that can we create a kind of a set? Can we create a kind of a set where all those congruency, angles, triangles, etc., will create one particular set which is called a topological invariance? That means everything will be within that abstract, lumpy kind of a surface. Now you see, Shabir and Veshak, those who are watching, I never try to forcibly introduce that you need to learn set, open set, close set. Are you observing this? I mean to say, through our discussion, automatically the concept of set came today. Maida, Vaishak, do you acknowledge to that? You can put it in the chat box. So the concept of the why do we use set, automatically now it is coming, because once we put a family of polygons into one particular abstract idea, then definitely we need to have a kind of a set, a kind of a subset of that superset, so that these areas are following the properties of that. And that has to be a smooth function, because I can get from this to this, and I also have to go back from that part to that part. So automatically the concept of sets are coming. So here it is, the property is preserved under homeomorphism. I'm not explaining homeomorphism right now, but most importantly, what we need to understand is that homeomorphism will come later. That this is what is actually our aim, that we replace the polygon to any shapes, and the concept of congruency of angles, triangles, isosceles, these, that, whatsoever, are replaced by a topological invariance. That means we need a kind of a set which will preserve those angles. Now here you see, I come to another important part of our discussion. What is the mathematics do I need to learn topology? Now I can tell you this much, that if you really are wondering that you need to have a very high level mathematics, absolutely not. I can tell you, you already know the mathematics which is required in topology. I will just show you. But the problem is the visualization. The problem is with the abstractness. The problem is to get our mind and brain get out of the idea of distance, angles, perimeters, polygons, all those maybe 12 years or 20 years that we have learned in our college or school, the Euclidean space, the Cartesian space, the coordinate system. We have to wash out everything, and then we have to grab hold of topology. I will tell you, it might be very interesting. There's a famous, this story, that a Zen philosopher was sitting, and a disciple came to that Zen philosopher. Okay, and he said that, Guru, I need to learn something from you. So the Guru told, okay, sit down, and he started to pour tea on a cup of on the coffee on the tea cup. And as he was pouring and pouring, it was constantly spilling up, spilling up, spilling up. And the disciple tell, oh Guru, what are you doing? The cup is constantly filling up. It is spilling out. The coffee and the water and tea is spilling out. So the Guru told, is a very famous, a very deep philosophical understanding, that the Guru told that I cannot teach you anything because your cup is already filled up. So we call this term in training, we call it, before you learn, you need to unlearn a lot of things. So topology is a kind of a philosophy that you have to unlearn a lot of things. If you come with your cup which is full, no guru can fill up that cup, because whatever I pour, it will spill out. How do you like this story? So the mathematics, what you need to know are these things. Tick means you have to know. Calculus, I think you already know. Even you don't have to go to three, one or two is good enough. Linear algebra, I kind of a thing you need to have the basic formulation. Set theory, yes. Reanalysis, yes. Differential geometry, not necessary. Group theory, not necessary. Any proof driven, my cup is half filled. Yeah. So you have to now make it absolutely empty, Vishnu. So the first one is definitely calculus. The second one, or I would say the first one is set theory. The second one will be building the basic foundations. And most importantly, what you need. So one, set theory, two, proof-based identical system, mathematical system. Third is real analysis and maybe a differential geometry. Shabir, you liked it, right? Yeah. So that's good. Okay, so and differential geometry not required right at this moment. Whatever the topology that we will deal with, it is not important. Now you see, if I have shown you this, now if you really don't have an understanding about set theory, please go ahead and quickly brush it up because that will be required. On the right hand side in blue, what it is written is very, very important. This is called mathematical maturity. And mathematical maturity, actually it doesn't come within 1 day, 2 days, or it is not actually done through practice also. I can tell you mathematical maturity, it comes as you grow. And also, mathematical maturity doesn't come that you do a lot of mathematics. I mean to say, it actually comes. You have that kind of an vision eye. You see things like that. So that is why I told that once you teach more, the mathematical maturity comes more. So today, whatever topology, etc., I'm teaching, I'm growing myself better. So that because you are asking questions, I am teaching. So now that is why we need what is called is a set theory. I hope now things are clear because we need to fill up all those shapes into different kinds of a set. Are you getting my point? Arithmetic or normal algebra or normal trigonometry won't be able to do, I would say, topology because these are all discrete measurements. An angle, a triangle, this kind of a harmonic analysis, real analysis. Are you getting my point? I'm not sure whether I'm very deep going inside. I'm trying to tell you that these mathematical measurements are very discrete in nature. They take objects and they analyze one by one by one by one. Differential calculus, integral calculus, linear algebra, whatever, trigonometry, basic arithmetic. But set theory, why we need? Because now we have to put those objects into a particular set, a kind of a basket, and then we have to see what is the property of that basket. And then we have to, from that basket, we have to find out the properties of other polygons and other shapes, and we have to measure them. I hope, am I clear? So no, I'm not boasting. Don't take me wrong that I'm saying that I'm great, but I can tell you that no professors, mostly the professors, they do not tell you that why set theory is required in order to learn topology. They would directly go and start doing with sets. Even the books you will see they start doing with sets. But first you need to understand what is the mental outcome, what is the outset of learning the sets. I hope this is clear, right? Very interesting story with a meaningful lesson. Okay, thank you very much. Yeah. My father actually told this story long back when I was very young. Okay, so now we come to the most important thing, and this won't happen in today's class. It's going to take more classes because now I'm showing you the basic idea of topological space. Then I have to show you the mathematical definition of what is a topological space. So you see that we need to define what is a topology. We need to define what is a topology. What is a topology? A study concerned with shape of and geometrical objects. Fine. Now you see, Vaishak, that's telling, okay, you agreed, right? So now you see that this Euclidean space, what we call as a Euclidean space, vector space, whatever that we are calling, now we need to extrapolate to a new world, which is a topological space. And we need to frame a new space. See, most of the book of Munkre, etc., they will start defining, let set X be a open set with this tau and etc. I will do that also. But first, let us understand that why we are moving to a new horizon, why we are new. I'm here to, as empty cup, you will teach me after that. Okay, fine, thank you. So now the question is that why I am moving to a new world of a topological space. Now, let me give you, I will move away from this screen and I will like to show you, or I like to explain you in this way. Now, suppose I am taking these shapes, for example, just two shapes, for example. Observe very closely, right? Please do pay attention. This is a kind of an intuitive understanding of topological space. Okay. Let me know if you're not being able to understand, because when I'm sharing my screen, I concentrate on my writing only. So whatever you guys are doing, I don't understand. So these are the two shapes. Fine. These are what? These are polygons. Okay. These are polygons. Okay. Now, what is my idea? My idea is that this side is equal to this side, or maybe this side is equal to this side. This congruency we don't want to define. We want to go remove those congruencies. Okay. Now you see, typically what happens is that if I consider this set, this polygons in one particular, you see, Vaishak, the name sets are automatically coming. You really don't have to do a lot of mathematics to understand this. You just to close your eyes and concentrate. So these are considering in a set. This is a set. I'm not saying that it is a mathematical set. Okay, it is a set, a thing which is holding these two polygons. Okay. Now I want to take another set. Okay, say for example, I draw a different kind of a color, this kind of a set, a place. Okay. Now, if I want to move these two polygons, say for example, from here to here, and if I want to move it from here to here, so what I need to do is that I may have to first say, first, you see, I will show you this on the next class, definition by definition, how things beautifully transcend what I am saying. Now, if I consider this to be a set, this one, this Euclidean set, and if I transferring all those things to a new kind of a set, first what I have to say that this new set should be a subset of this big set. Number one, obviously. Because if the polygons are in a Euclidean or whatever kind of a set, then it has to be a kind of a subset of that set. Number one. Also, if I take a set which is empty, right? Sorry, my handwriting is too bad over mouse. It's fine. This is an empty set. That means no polygons are there. That set also have to come in this set, right? Because this is an empty set, and it might happen that in Euclidean space we call it an empty space. It is an empty space. Are you getting my point? I have studied now set in 11th NCRT. Is it enough? Okay, I will come to this question later. Let me first explain. So if I consider a set in Euclidean space, which is an empty set, I mean to say there are no polygons. It can be an empty set. That means this empty set also have to come over here. So already we have started to define this, which is called a topological space. The rest of the definition I will come later. But one thing, I hope it is very clear to all of you, that if I take a set which contains these polygons, this set obviously have to be a subset of this. If I take a set which is phi, that is, it doesn't contain any set, it is an empty set, this has to be there. And there are certain things which are union and intersection, that this one should be intersected with this, which will carry another, and this will also have a union. All those things I will come later. Am I being able to clear? I don't know, you are not telling me anything. Have you been able to get it? If I already considered the Euclidean space in all these polygons in a kind of a set, then if I create a new set, which is the topological space, then obviously you got it. Vaishak, are you there? Are you getting my point? I mean to say, I cannot call one by one, but anyway. So if I extrapolate it and take it in another kind of a topological space, then obviously that has to include that set, number one. And also the empty set has to include that part also. Shabir Safi is telling I'm getting. That also has to include that set. So empty set has to include, that set has to include, and if there is an union, that means all the objects of the set are getting close together. And if I'm getting, yes, yes, is this a generalization? Yes. I am coming to that generalization part, Rajkumar. What I'm trying to show you, I'm not going to the mathematical definition right now, Rajkumar. Are you getting my point, Rajkumar? I'm not going into the mathematical definition right now. I'm just showing you geometrically and intuitively how we got. First of all, the word set theory automatically comes in because we have to categorize the polygons in a set. Now, if yeah, you're getting it. Very good. Very good. Okay. So, and then if I extrapolate it to another, then I am Rahat Pirazda from Lahore, Pakistan. Okay, Rahat, very, very good. Very welcome. I think you have missed a very important part. Request you to go back and watch this video because it will be on my channel. So that part is also coming, right? Okay, yeah. And also, if I taking the union, I'm not taking again the union as we mean by set theory. I'm taking that all those objects are coming close to each other and they're forming a set. They're intersecting with each other. So all those have to include into that kind of a set, right? That means obviously we need to have a set theory which will save us from dying. Which will save us because no other differential, integral calculus, trigonometry, mathematical analysis, nothing would create that kind of a mathematics which set theory does. And also you see in real analysis also we use a lot of set theory because real analysis is also kind of a generalization of the calculus, of infinity, of continuity, of divergence. Vaishak is telling I can understand, right? So I think all of you can understand. So this is the concept of creating a new topological space out of that Euclidean space, include those things, include empty set and all other properties. Now you might say that why those properties are used by union and intersection? Why not plus and minus? Also there is a reason. And the reason is that the moment we start doing the arithmetic operations over that, that means we need to have distinct objects and their properties. And remember, I told you right at the beginning of this class that we need to group them. We need to make a lump. We need to create an abstract idea. So we won't do those, plus and minus. Rather, we would do intersection and union and disjoint, etc. Try to understand the mathematics is moving. I mean to say we are generalizing as Rajkumar has told. That generalization is not only in terms of abstract thinking or abstract, I mean to say abstract ideas. The mathematical operations also have to change. You cannot say one polygon plus another polygon equals to second polygon. You have to do a union. Why you're doing union? Because those objects won't be separate or distinct object. They will be lumped up in a kind of a crazy abstract objects like this. Are you getting my point? All of you. I will get an object like this. So how can I this plus this? Rather, I use this one and take a union of this one. And I take another object, something like this, and I do an intersection with this another object. First is most important in topology is to get a visual intuitive understanding. And then when you go into the syntaxes, or I would say when you go into the set all those things, it will be easier. So whenever she said a set S, okay, set S, that means there's a box which contains all those things, is a subset of another. The question is that why do we need a subset? Obviously because we are generalizing. So if that set contains everything, including all the polygons of the world, then obviously creating a topological space will have to have a subset. Clear? All of you? So here you see that Euclidean space, a space in which the axioms and postulates of Euclidean geometry apply. Metric space is what? A set together with a notion of distance between its elements, usually called points. The distance is measured by a function called a metric or a distance function. Isn't it so beautiful? And that is why I feel and I love topology. Okay, I am skipping these two slides, okay, because here I have mentioned the definition of metric space. I will come to that later. This will also later. Here you see, this is very important. Why it is important? It says that the Euclidean space first gets generalized into metric space. That means metric, distance, d, dy, dx, all those things. Then metric space gets generalized into topological space. So the real numbers with the distance function d, that means if I get a 2 points, okay, and there is a line, I say this as d. That means we are using again distance, that means metric. But in topological space, you see generalizes structures, concept of distance is replaced by closeness. Here comes the beauty. The concept of distance is replaced by closeness. That means, sir, recommended any books for introduction to Riemannian geometry for physics student? I don't remember BSKR You can just contact me a little bit later once I'm done with the class, because I'm very intensively teaching topology. I will tell you what is the book. There are good notes on Riemannian geometry. I will let you know. Don't worry. I will tell you. So the question is that the distances. What I just forgot what I was telling about. Uh, yeah, the distance of closeness. That means again I am not moving from one point to point, rather I am telling that how I am close to that person. If I can say I am close to that person, that closeness will itself define distance. Are you getting my point? And this closeness cannot be defined by normal arithmetic, normal mathematics. That has to be done by sets. Closed with respect to what? With respect to something, right? So this is why it is very important. Now here I will show you. You see, this is a very important figure. So how do we make a definition in topology? Say for example, this frog on the left hand side, we know it is an aquatic anuran leaping amphibians, right? For example, a large cat, mane, it has got a mane, social species. Then we have a cat which is carnivorous, lonely. But a lion cannot be the same as the tiger. That means what? That means it has to certify it has to satisfy certain definitions, and this definition is what we call as a topological definition. That means each feature that we try to make it should have a kind of a feature. Yesterday, if you have noted, I talked about abstract topological algebra, where I showed you that we need to define it in specific groups. Here also you see that this particular frog, I mean to say, has got certain features. That is why it is an amphibian. This is a large cat, and there is another cat which is the tiger. But these are not the same. So that means we have to define a definition followed by certain conditions. Here you see x equals to ABC. If I take it as a set, okay, now those are points. Remember, but we won't be using the term point here, but we would be use the term closeness. I will come to that, but just to tell you, for example, A, B, and C outside is a topology. A with BC is a topology. ABC is a topology. Now you see, if I take this kind of, okay, let me show you. If I just take copy and paste it over here. Okay, I will just try to show you what I'm trying to do, because I cannot lose my cursor over there. That is a presentation. So if I take this, now you see, okay, let me take a different color so that, yeah. So from this point to this point, or from this point to this point, or from this point to this point, or to this point to this point, I cannot use the word distance, because again, that distance would mean I am using a metric. So what I would use the term, I would use this term: closeness, neighbors, compactness. These terms will slowly evolve, don't worry. So this is called closeness. Okay. And what's most important thing, you see, all these are taken in a set. This is also a set. Why I'm taking a set? For this reason, that we are now putting the polygons or whatever objects in one particular set, so that we can understand what those sets behave, and then we replace the definition with closeness and understand those things. I hope it is clear, right? It's clear. I mean to say, are you getting my point? So this is how. Okay, so that's all for today's class. Tomorrow I would be speaking on what is called a orientable and a non-orientable surface, and we will explore that. What is a Mobius strip? What is a Klein bottle? Again, what I'm trying to do for one or two more classes, I will give you a very overall understanding of topology, a very, I would say, a kind of an intuitive, counterintuitive, a geometrical thing, so that do you dream topology when you go to sleep? So when you close your eyes, when you're sleeping, you will see those beautiful objects coming in front of you, going around like this. So that is how it happens. And I already gave you a hint that why do we need a topological space? In tensor space, there is no distance. It is closest or farthest because it's said. No, 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 no. Yeah. Anyway, this is a different kind of a topic. I will talk to that later. So the thing is that all those things. So topological space, why? We already got what is a set. We also understood that why do we need a topological space, and we understood what is the concept of invariant and why we are using this term closeness, compactness. We will explore. Don't worry. Closeness is not a simple thing. Closeness, compactness, neighborhood, all those things we will explore, right? So that tomorrow we will, the tomorrow would be the last, I won't say last, I would say tomorrow would be the last intuitive class of topology, I can say. We won't be discussing anymore about those abstract concepts. Then from Saturday and Sunday onwards, we will go into the direct mathematical definitions of what we call topological space, etc. And thereby we'll, now when we go to those mathematical definitions, automatically you will see these concepts will come. I will first put the definition on the Jamboard, then I will draw pictures to make that mathematics understandable. And remember one thing, that in case of a topology, we have to, oh no, I am late, parity physics. No, you're not late. This video is there. Please go ahead and watch, because I have already covered one or two. Vishnu, is it the first video, a second video of topology? Vishnu, you can tell, or this is the third, I think. Anyway, so please, geometric algebra and algebraic geometry lecture. Yeah, we'll come to that. Don't worry. Let me complete one by one, because I'm the one person who is doing all those things. So just have patience. Geometric algebra, algebraic geometry, I will do. First, we are doing topology, so let us first complete this one by one, then we will do. So that part will be done by tomorrow. You will get a complete understanding. We will quickly review the entire understanding of topology. So tomorrow's class will be completing this and then brushing up whatever we have learned about topology from first and to the last. So anybody who has missed this, I would request not to miss tomorrow's class, because tomorrow's class will be a very overall idea, but everything will be discussed. Your courses are coming amazing. Thanks for the effort. Okay, thank you. Yes, third class of topology. Yeah, Vishnu is right. It is third class of topology. Okay, so yeah, so the thing is that then we will brush up all those things, and then from next week we will jump into the mathematics of topology and go on. And also we will be starting with tensors. I don't know how we are going to manage all those things. My goodness, I don't know. All those things are coming up anyway. Okay, so thank you very much again. Thanks a lot, and I will announce a surprise by tomorrow, because that very amazing and a very, I would say, renowned professor has agreed for a podcast coming up very soon. Well, no, that won't be on topology. Yeah. Book's name, yeah, just contact me later. I don't remember. I have to just look into my library. I will just let you know. Thank you very much. Thank you for watching. Just share as much as you can, because I really want to know that. Yeah, that would be great. Parity, I would request you that you please quickly watch, not much of mathematics, etc. Just quickly watch that and don't miss tomorrow's class, because we are going to sum up everything that we have learned. And before I go into the mathematics of topology, I hope you are all enjoying, isn't it? But you should put up comments. I mean to say, contact in Gmail. Why? Contact.physics for student. I have received your Vishnu Tripathi, right? I've received your email many times. contact.physicsforstudents@gmail.com. This is my email ID. Okay. Frankly, tell me, are you all enjoying, or is it that, okay, I am speaking, so you have to listen? You can put it up in the comment box. You can tell me that what are the ways you want things to happen. Because I think that we are doing with the topology for the first time, isn't it? That we have got live classes on topology, and I'm trying to teach in a very different way. So just wanted to know how you guys are, quickly put up in the comment box. 1 minute or so, I will end the live session. So are you guys all enjoying? Could advise us which book is good? It depends upon the level. I would first say go for Munkre's book, and there is a wonderful book called Topology Without Tears. That is by I don't remember the name of the book. Is Topology Without Tears. You can start with Munkre's book. Okay, do one thing, Rachid. Just hold on for a second. Just a second. Just a second. Just hold on. I will just give you. Just be there. I will tell you what you're looking for. Okay, here I give you the entire playlist of topology, Rachid. You see, everything is given: which book to read, what mathematics to know, basic lectures on topology, topology and topological space. Just copy this from the chat box and paste it on your YouTube. I mean to say, in the internet, you will understand. Every single thing is given here. All those things for last 1 year I have been doing. So what book to read, which book to read, what are the mathematics that you need to know, all in itself. So Vaishak, you are enjoying this, right? So just to ask you, it is a little bit different. I think, are you getting what I'm trying to tell? Live class is very interesting on join. Yeah. So what I'm trying to tell is that I'm trying to make things a little bit different. I study tensors for GR, but I need Riemannian geometry for further theoretical like in algebra. That is what I'm asking. Yeah. Oh, books on set theory, any book, any books, any book. Set theory, you can pick up any textbook. I think, Rachid, if you take up Munkre's book, okay, set theory is actually taught before going into topology. That is the uniqueness of Munkre's book. Right. If you start reading Munkre, you will see that he will first teach topology, and then he will go into, he will first teach set theory, then he will go into topology. BSKR, you contact me in my email and WhatsApp. I will tell you what are the very good books. I've got a good notes also. I don't remember right now. Okay, so that's it. Okay, Rachid is telling we are enjoying your lecture. So Rachid, where are you from? I mean to say, are you from India? So fine, thank you. So I won't waste time for you to hear me over. We'll come up tomorrow, sum up everything, and then we will start with the actual mathematics. Oh, you're from Canada. Okay. I'm so sorry. Yes, yesterday you told me. You're watching from Canada. That's wonderful. Okay. So I think, just to tell you, because you're all watching, I think I have paused making videos and doing more of live classes. I think I've made a right decision. What do you think, all of you? Because you are the subscribers. It is just because of you I am growing, the channel is growing, and everything is happening. Don't you think that in videos that there is a restriction? You make the video, speak for a certain time, that's all. But explaining things more like this Jamboard, all those things, I think it is better in the live classes. So I think that more than the videos, the live classes are really very good. Vishnu has already told, Rachid has already told. I think others also do. You agree? Because I am also in doubt that I have stopped making videos for some days. Shall I continue making videos, or shall I continue with the classes? So I was in a dilemma. So I think that you can just put it, and you let me know what do you feel. Maybe not now, maybe later. I feel that interacting, asking questions, all those things, live classes are much, much important. And it gives for me also a better teaching. What I cannot do, yeah, Vaishak also agreed. What I cannot do in video, I can do a lot in live classes, frankly speaking. Yeah, Parity is also agreeing that live classes. Okay. No, I was, feeling bad that what will the subscribers feel that, sir, have you stopped making videos? What is going on? Because you stopped, because the channel is meant for videos. So I think that I should concentrate more on live classes every day, dividing this into 1 day topology, 1 day tensor, 1 day linear algebra, etc. I think that is very good. Yeah. So thank you very much. I got a poll from all of you that live classes should continue. and I hope you don't mind that I am not making videos anymore. I will make videos, but I think what I can do more in videos, I can do more in live class, and mostly interaction becomes better. Like BS Card is asking a question on Riemannian books, etc. I think that's so. Anyway, thank you very much. We'll be back tomorrow. Yeah, 9:15. Yeah, 9:15 will be okay. Yeah, 9:15 will be okay. Tomorrow I got a work from home, so I think I can manage time. Yeah. Goodbye. Take care. Thank you for participating, all of you. Goodbye. Take care and enjoy your holidays.